Now we go into the details of different methods of evaluating the integrals. Mainly there are three methods on high level to evaluate the integrals. First is the substitution method, which is a very powerful method, and based on these methods we will develop lot of standard results. Second method is called as integration by parts, which we use to evaluate the integral of product of two different functions. And lastly we have the integration using what is called as partial fractions, which involves the rational algebraic functions of specific nature. So let us go into these details one by one. The first method is the substitution method, and here is the statement of what do we do in that. That is, let x be a differentiable function of t. That is, we can denote say x by phi of t, which is some function of t. Then integral of f of x dx can be written as integral of f of phi of t multiplied by phi dash of t dt. So what it means is, if we replace the x by phi of t, then dx will become phi dash of t times dt. That is nothing but, if you differentiate this particular expression, you are going to get phi dash of t dt. So therefore on substitution, x becomes phi of t and dx becomes phi dash of t dt, isn't it? So that is the formal statement of substitution method. In actual examples we use the substitution in the opposite direction. That is, often we will be given the question which involves the pattern something like this, and what do we do is we try to find out which is that particular function phi of t which we can replace with a single variable x. So we must also have in the integral the derivative of that particular function, which can be replaced with dx, right? So the important point to remember is, we must look for certain function or certain expression which can be substituted with a new variable, and similarly the derivative of that expression also must be present in the numerator of that function to be integrated. So let us see few examples so that this process will be clear. Now here are few corollaries of the substitution method. That is, these can serve as an examples also. That is, suppose we are to integrate first f of x raised to n multiplied by f dash of x dx, right? So here let us assume that, suppose for the time being, we call this function of x as say t, right? So in that case, if we differentiate f of x equal to t, then by chain rule we will get f dash of x into dx is nothing but dt, isn't it? So therefore the function that we want to really integrate is t raised to n with respect to t, and we know that the integral of t raised to n is nothing but t raised to n plus 1 whole upon n plus 1, because that's a standard result. So therefore lastly we can replace back t with f of x, so therefore we get the result as shown here. Similarly in the second one we have f dash of x upon f of x to be integrated, and the answer is log of mod of f of x. That is, once again, if you replace f of x with t, then f dash of x dx becomes dt. So therefore what we want to really integrate is 1 upon t with respect to t, and integral of 1 upon t as we know is log of t. So on replacing back we get log of f of x. And in the third one we have integration of f dash of x upon root of f of x, which is nothing but equal to 2 times root of f of x, which again follows from the same case. So a very important point in all of this to be remembered is the derivative must be present in the numerator in all the three, if we carefully observe. So in substitution, what we actually try to do is we try to look for certain function f of x which might be present in numerator or denominator anywhere, but on replacing that function with say a new variable t, the derivative of that function, that is f dash of x, must be present in the numerator only, right? So this is a very important point to be remembered. Alright, so now let's see few examples based on the substitution method. Here we have to evaluate the integral of sine cube x into cos x dx. So let us once again recollect what we want to do in substitution. Are we able to spot any function which can be replaced with say t, and the derivative of that function is present in the numerator? So here we can easily see that if we call sine x as t, then the derivative of sine x is cos x, which is correctly present in the numerator as we want. So therefore we can definitely go ahead with the substitution, and let us say that let sine x be called as t, that's what we substitute. Therefore on differentiating both sides we get cos x dx as nothing but dt. So therefore our given integral becomes, since we have sine cube x, that becomes nothing but t cube because t is sine x, into the next part, that is cos x dx, simply reduces to dt, isn't it? Now this becomes a very standard function, that is t raised to n type of function. So therefore the answer of that is t raised to 4 upon 4 plus c, and at the end we must replace back t in terms of x because t is what we had brought on our own. So t raised to 4 is nothing but sin x raised to 4 upon 4 plus c. That's the answer. So this is how we solve this question by substitution method. Right. Let's see next question. Evaluate 2x plus 5 upon x square plus 5x plus 2. So once again, can we see some function present somewhere such that its derivative is present in the numerator? So it won't take long to realize that if we call this function as t, then we are clearly seeing that the derivative of this particular expression is nothing but 2x plus 5, isn't it? So therefore if we call x square plus 5x plus 2 as t, then we know that 2x plus 5 dx is nothing but dt. So therefore our integral is nothing but 1 upon t dt, correct? Because this whole portion 2x plus 5 dx becomes dt, and we know that integral of 1 upon t is log of mod of t. So therefore the answer is log of mod of x square plus 5x plus 2 plus c. Right? Now often these rules can be directly used in the examples. Since we are doing it for the first time, we are actually writing it like substitution. But just to recollect, we have seen the result that if derivative is present in the numerator and function is present in the denominator, then the answer is straight away log of that particular function, right? So this is how we use the standard result. Now let's see one more question based on this. Now here we have to evaluate integral of e raised to x plus 1 whole upon root of e raised to x plus x. Now if we compare this with the standard corollary, that is f dash of x upon root of f of x, isn't it? Because if you observe, the derivative of this particular expression, that is e raised to x plus x, is nothing but the expression which is already present, that is e raised to x plus 1. And we know that the integral of f dash of x upon root of f of x is nothing but 2 root f of x plus c. So therefore the answer of this question will also be nothing but 2 root e raised to x plus c. So that is how we use the substitution method and its corollaries.